Today we'll continue the story of categorifying prime roots of unity. And recall, yesterday we introduced this very small but useful half algebra H, which is over a field of characteristic P. And this is just generated, the truncated polynomial algebra K generated by D, quotient the half ideal of D to the Pth power, so that it's a half algebra where this differential D is a primitive element in the sense that delta of D is D tensor 1 plus 1 tensor D. Okay, so, and we'll call the category of graded modules over this half algebra P complexes, and the stable category, which is obtained by this module category quotienting the class of projective injective modules, the stable the homotopic category of P complexes. And the reason why we care about these two categories is because of the following very simple observation of Bernstein and Khovanov, that both categories are monoidal categories, so they have a tensor structure because H is half algebra. And it's furthermore, when you pass to the stable category, it's tensor triangulated, and this triangulated category categorifies the ring of cyclotomic integers OP at a pth root of unity. So categorification means that, well, when you pass to the Grothendieck group, this direct sum, tensor product structures, etc., become addition, multiplication, etc., etc. Okay. Again, this is supposed to be introductory course, so I'll give you a sketch of the proof why this is true. So this is how, in general, you work with tensor triangulated categories. So you want to show that first off, this descends, this tensor product on representations of H descends to the stable category as follows. So you want to show that modules that you have annihilated are, when you take tensor product, is still are modules that you want to annihilate, so that this is a tensor ideal. And projective injective objects do form a tensor ideal because when you take tensor product with an arbitrary module, this is still injective. This is because of the tensor Hom adjunction we mentioned last time. And furthermore, you want to show that this construction commutes with homological shifts. And remember, last time we defined homological shifts by choosing an injective embedding or projective cover of this module, and the quotient is declared to be the homological shift. So when you tensor an arbitrary module with this short exact sequence of H modules, again, this is you get a short exact sequence of H modules. So the middle guy is injective, so this is the quotient is going to be the homological shift. And then you want to verify that this tensor product structure commutes with distinguished triangles. Again, remember how distinguished triangles were constructed. Well, you form the cone push-out diagram of this embedding into injective and arbitrary H module homomorphism. And this part was the distinguished triangle. So when you form the tensor product, the whole thing is still a push-out diagram. So you it commutes, this tensor product commutes with distinguished triangle. Okay. And finally, why this is the Grothendieck group is therefore a ring for arbitrary. If you are given a finite dimensional half algebra, this stable category is always a ring, and the multiplication structure is given by tensor product, and the multiplication unit is just 1. So for this particular half algebra, it's a local half algebra. So this Grothendieck ring is generated by just simple modules up to grading shifts, and the only relation we have annihilated are shifted grading shifts of the free module. So the grading shifted copies of the free module have symbol which is q to the I times the cyclotomic polynomial. So when you quotient this ring ZQQ inverse by this cyclotomic integer ring, you get the cyclotomic polynomial ring. So that's why That's why this is a categorification of this ring of cyclotomic integers. And so the main part of today's lecture is how do we utilize this categorical incarnation of OP. And in what follows, I'll try to outline a story. So how do we categorify modules over OP? And you're not just interested in arbitrary modules or algebras over OP, but instead things that we're really interested in, for instance, the quantum group roots of unity that we want to categorify, and quantum group representations that we want to categorify. So this is what I'll try to outline in today and tomorrow's lectures. Okay? All right. So to do this, let's try to generalize homological algebra slightly further. So how do we, before trying to categorify algebra objects, try to build algebra objects over P complexes, how do we categorify modules over this ring of cyclotomic integers? So let's again resort to the usual homological algebra for some hint. So in the usual homological algebra, how do you build interesting invariants as abelian groups? So whether it's taking homology or K-theory of some category, well, usually this arises interesting modules arising as invariants of varieties or categories come in this way. So it's K0 of some abelian category that can be written as A modules, or K0 of some sheaf category, whether it's coherent sheaves or constructible sheaves, doesn't matter. But what's nice about these categories is that they all admit a description in homological algebra as modules over certain, or differential graded modules over some dg-algebra. So you can take some generator of these categories in a derived sense, so dg sense, and take the endomorphism algebra, it becomes a differential graded algebra. So all such categories can be regarded as differential graded algebra modules, or their relatives of A infinity algebras. So what's a differential graded algebra? It's just going to be an algebra object in the category, in the homotopic, well, in the abelian category of H modules. Here H is a dual numbers. So it's going to, a dg algebra is just a graded algebra equipped with two nilpotent differential such that it's a super differential D of, so as assigned to a dg algebra, you have the usual notion of dg modules over this algebra and homotopic category, derived category, etc. So you can construct these interesting categories out of dg categories, dg algebras. So now let's seek an analog of this construction in the P complex world. So in characteristic P, a PDG algebra is going to be a graded algebra over a field of characteristic P, equipped with a degree 1 nilpotent differential dA, such that d to the pth power is identical to 0, and d acts as a derivation. And you should notice that there's now no -1 to the degree of A, because this Hopf algebra of kd over d to the pth power is a genuine Hopf algebra. It's not a Hopf super algebra anymore. So it's the lack of minus sign makes a lot of computations a lot easier in the PDG world than the DG world. So you don't have to bother with a lot of annoying signs. So similarly, a PDG module is over a PDG algebra is going to be a graded module equipped with the endomorphism and dm, such that dm to the pth power is identical to 0. This is dm to the so is compatible with the A action in the following sense. Okay.
Okay. Example.
Yes. Examples. So what are some naturally arising DG algebra, PDG algebras? So for instance, the polynomial ring over a field of characteristic P, you can define a P differential just by setting d to the x equals x to the square and extend it to the entire algebra by the Leibniz rule. So if you have dx to the 8th power, it's going to be A times So I should write down something maybe. Oh, there's no chalk. Yeah, thank you. Yeah, using the Leibniz rule, you can easily see that d to the x arbitrary power is going to be a times x, the a plus first power, just as in calculus 1. So therefore, using this formula, you can see that over a field of characteristic p, d to the pth power is identical to 0.
Why is that power bigger?
Yeah, power becomes bigger. This d is really the action of dx squared ddx. Okay. So in this way, this becomes a PDG algebra. Okay. Similarly, if you want a non-commutative example of PDG algebra, if you can take the usual. Sorry. Why is d squared equals 0? This is just a small computation you can do. For instance, in characteristic 3, maybe d squared of if you want to check on the generator, d squared of this is d of x squared is going to be 2 times x cubed, and then d cubed of x is d of 2x cubed is going to be 2 times 3 times x to the fourth, and in characteristic 3 this vanishes. Yeah, d to the pth power equals 0. Okay. And similarly, if you have an algebra A, by a matrix algebra, if you have a direct sum of Jordan matrices with diagonal entries 0, so nilpotent Jordan matrices, and you can take the commutator with this J, and you can easily, if the Jordan sizes are all less or equal to P, you can verify that because J is a nilpotent, P nilpotent matrix, then this is a PDG algebra. Okay. So if you have two PDG algebras, their tensor product is going to be a PDG algebra. So the polynomial ring in n variables, generalized in this case, is going to be a PDG algebra. And the original differential d of, in the first example, sending xi to xi squared, commutes with the symmetric group action. So this differential is entirely symmetric. So in particular, you have a symmetric polynomial as a PDG subalgebra sitting in the n-variable polynomial ring. So this is another way of constructing important symmetric functions has a PDG algebra structure. Okay. So this example is quite important that will plays a fundamental role in categorification. So we'll come back to this point later. All right. So just as let me draw some diagrams indicating the analogy between the usual differential graded algebras and this characteristic P analog. So starting with the dg algebra or PDG algebra, you can consider the abelian category of dg modules or PDG modules. And once you model null homotopy, you get a triangulated category of the homotopy category. And earlier we explained what's the analog of taking cohomology is. Taking cohomology is just forgetting the A module structure and passing to the stable category of H modules. So then the notion of quasi-isomorphisms makes sense. So you can invert quasi-isomorphisms to get the derived category of PDG modules or DG modules. So of course, this generalizes to arbitrary finite dimensional Hopf algebra. So therefore, my former advisor, Khovanov, coined the terminology. It's a combination of the study of Hopf algebras and homological algebra. So he called this Hopfological algebra, this subject. Okay. So why this is relevant to categorification is that, well, the derived category or even homotopy category of PDG modules admit a categorical action by this tensor triangulated category in the following sense. So if you have a PDG module and tensor with the P complex, it still is a PDG module. And when you pass to the Grothendieck group, this tensor product action gives you the action of the ring of cyclotomic integers on the module. So this is in this way. This is categorifying some module structure over this ring of cyclotomic integers. So if you replace this diagram by the usual Hopf superalgebra of dual numbers, this is just the usual Z action on the Grothendieck group. So here we specialize to the case. Here a caveat is, well, we have to, whenever you work with dg-algebras, you don't want the Grothendieck group to collapse too much. So you have to impose some compactness condition on the class of module you consider. So this is a mild assumption. So this is the compact derived category of PDG modules. It's okay. So you want to avoid allowing infinite modules that trivially will collapse your Grothendieck group. Okay. So now let's move on to how do we categorify? How do we build more interesting algebra objects over the cyclotomic category? So or P complex category. Why? And to motivate this, why do we want to categorify this? Why do we want to categorify the quantum group, in particular this quantum group Y.Qi? As in yesterday's lecture, we explained this is the quantum group that appears everywhere in Witten-Rasch-Lincoln-2IF story, but what's the role played by this quantum group? So this quantum group is a quantized. So it's in Chern-Simons Witten theory, SO2 appears as the local gauge group of this 3D Chern-Simons theory. So you impose gauge transformation condition on your underlying three manifold or three manifold with the link removed, and so this is after this procedure of performing gauge theory, you come up with local state spaces that's acted upon by the quantum group. So if you have a three-dimensional ball with the 4 points removed, what do you assign to that three-dimensional ball with a tangle removed is precisely a representation of Y.Qi, and the braid group acts on it, and that gives you a way of constructing non-link invariants as done by Jones. So Y.Qi is sort of the quantized gauge group in Chern-Simons theory. But the quantization process is very sophisticated. It uses Chern-Simons functional as a special case of what we have seen in Phil's talk yesterday. And so, as in Crane and Franco's conjecture, if you can lift this process to a 4D theory, maybe this categorified quantum group should play the role of a quantized two-gauge group. So whatever that means. So actually figuring out what this means right now is still an open problem. So what is, and this problem is phrased in Crane and Franco's original paper as what is the Hopf category, and there's no definite axioms for this construction yet. All right, so let me give you a biased review of what quantum group of SO2 at roots of unity is. So as quantized gauge group. So quantum groups are local gauge, local symmetries of quantum states. So we're going to draw pictures for this quantum group. We're interested in a very particular version of quantum SO2 at roots of unity. This version came from the version of Bellinson, Lustig, McPherson. So where they converted the K part, the Cartan part, into idempotents. So instead of the usual E, F, and K generators, you don't see K, just E and F. So what are E and F? So well, we're borrowing some pictures from, as we have seen in Theo's talk yesterday. We're drawing everything on the one-dimensional line. So you just think of one-dimensional line as an open interval, and the quantum operators will just switch quantum state from lambda to lambda minus 2. So this is what F does. It will just imagine if you have some quantum states living in this one-dimensional infinitesimal neighborhood, once you pass through this down arrow, this quantum state will decrease by 2. And similarly, when you live in this world, lambda, once you pass through this up operator, it will go to lambda plus 2. It's very similar to what you have seen in like spin chain picture in statistical mechanics. So this is, we're borrowing that kind of picture over there. So, well, what's the algebra structure? So you have very easy generators for this kind of pictures, and where lambda ranges over arbitrary weights. So lambda are just integers, parameters by integers. The algebra structure is just given by concatenating or stacking pictures side by side. If the weights match, from the rightmost weight match with the leftmost weight of this picture, you just put them together. If they don't match, you just declare them to be 0. Okay, so this picture will describe a chain of quantum states change from mu plus 2 to whatever this is on the leftmost side. Okay, so in this way, this quantum group will dictate how quantum states change from one eigenvalue of k to whatever you see on the left-hand side. Oh, so this is a generator description of quantum groups. So you need some relations, impose some relations. So the first relations are how do you commute two operators, this lowering operator and raising operator E and F. So they commute at the cost of adding some lambda with nothing in the picture. So this is, remember, this is lambda. So here in the middle, you will see lambda minus 2, and here it becomes lambda again. So if you commute these two, you will have quantum lambda many of doing nothing in here. And similarly, when lambda is less or equal to 0, you have this relation. Yeah. Previous. This is just the usual algebra multiplication of a, yeah. It's just you see when these two weights match, you just glue them together. If they don't match, you just declare it to be 0. They cannot be multiplied. Okay, and so this is the usual EF commutator relation in the Lie algebra. And finally, for quantum group at roots of unity, you have this very important nilpotence relation that's at a kth root of unity, you declare that e to the kth power and f to the kth power to be 0, so that it's you have this nilpotence relation. All right, so how did this quantum algebra get categorified in the sense of Khovanov-Lauda and Rouquier? I'll give you a description of how this was done in the sense of Khovanov-Lauda and Rouquier. So to categorify quantum groups, what do you want to introduce as in the description? This is the study of topological field theories. You want to introduce an extra dimension in the picture. So that's the time evolution picture. You want to study how quantum operators or quantum states evolve with respect to time. So instead of having the commutator relation between these operators, you want to say that this operator can evolve into this entire picture, and whatever picture you can draw in there to fit this, to describe this evolution process. Okay, so let me give you the answer due to Khovanov and Lauda. How this. So the rough idea is one-dimensional pictures, or we're going to draw two-dimensional pictures. So each horizontal slice of the two-dimensional picture is going to be an isomorphism. Is going to be the quantum group, the decategorified quantum group picture. So each 1D picture is going to be a horizontal slice. It's an isomorphism class of projective modules. And 2D pictures will be maps describing homomorphisms between the 1D slices. And the sum of 1D pictures will be symbols of direct sum of modules. And equality will be become isomorphism of modules. So this is just some rough sketch of the roadmap, how you can do it. So let's look at this explicit example. So how does E evolve into, for instance, how does E evolve into itself? You have to have an identity morphism from E to itself. So we just draw this picture by just a straight up line. Doesn't do anything to E. But when you have two copies of E squared, so two up arrows, it will evolve into itself. You're forced to introduce this crossing generator. So this will send this copy of E to that and this copy of E to that. Okay, and miraculously this. Sorry, I should have drawn the dots here. So this is E together with the dot, and these two generators will are subject to the so-called Neo-Heck algebra relations. So whenever you see two copies of E composed with dots, so the different ways of composing with dots will result in the identity endomorphism of E from E to E. Yeah.
About the reflection positivity.
Sorry?
Reflection positivity.
Reflection positivity?
Yeah,
here there's no yeah, this is a pseudo time. There's yeah. And the new part of this algebra means that this generator squared is 0, and it satisfies the Braid relation or Yang-Baxter equation. This is for this operator E evolving into itself. So this algebra is actually pretty famous. Has been intensively studied in the 80s by the work of Kumar, and I think this is called the Neo-Heck. What's that? Dot. I forgot to draw this. This generator should carry a dot, so it's just an endomorphism from E to itself. Okay, so this is just describing how E can evolve into itself, but how do you connect E and F's? So to connect E and F, Aaron Lauda introduced these cups and cap generators. So it goes from E composed with F to nothing. So here's this diagram I just indicated by a horizontal arrow. Just means there's no operators here. So it goes from E composed with F on this horizontal slice to nothing in here. And similarly, you have this generators from FE to the cups and caps with all possible orientations. And together with the Neo-Heck algebra generators, cups and caps are bound to satisfy this relations. So they're bijoint. The up crossings are bijoint to the down crossings. And using the cup and cap, you can cook up this bubbles. This so-called bubble is a cup and cap, and together with some dots. And these pictures represent endomorphism of the identity map. So they're like the central objects in this category. You require them to be have positive degree. So this is so it turns out these bubbles are quite important and related to trend classes on some infinite Grassmannian. So that's why we need to impose that their degrees have to be positive, because they will represent trend classes in geometric pictures. And finally, if you have this kind of picture cooking up a curl out of this is identity cup and crossing and cap, then you can reduce to bubbles together with these dots. Okay, so you can simplify pictures using this way.
So here is the symmetric reverse. Okay, about the non-reversible, non-invertibles. Here is non-invertible symmetry. Can you understand the bubbles?
Non-invertible.
Non-invertible symmetry. Category symmetry. Non-invertible. Here's an invertible symmetry.
Well, these generators are not isomorphisms So they're not invertible in general.
In this sense, you don't have any kind of non-equal space.
Yeah. And finally, this key identity decomposition relation that will lift the commutator relation of E and F we have seen before. So this is the identity morphism of E and F is the same as this picture. You see that this horizontal slice is still E and F, but in the middle it factors through F and E, and here in the middle it factors through nothing. So bubbles you can move up. So in the middle there's really nothing. Circle with the number. This is just a shorthand notation for this picture. It's just cap with the dots. I just want to record its degree so that it's this two times k is really the degree of this bubble. But there are two versions, clockwise and counterclockwise. It's 0, yeah. If k is less than 0, in these numbers, it's going to be 0. Okay, so yeah, number of dots. This picture is really just a shorthand notation for m dots. X to the mth power. All right. So, well, the theorem of Aaron-Lauda, which is a special case of Khovanov-Lauda and Rouquier's construction in the SO2 case, is that this graphical calculus, which we denote, or it's just going to be a two-dimensional algebra. You have horizontal multiplication, vertical multiplication. So we just call it a two-dimensional algebra. Or more formal language is this is a two category, is denoted U is this relations are non-degenerate and categorifies U dot SO2 at a generic Q value. And proving the non-degeneracy of this calculus is just as in the usual representation. When you define something by generators and relations, you have to find nice enough representations for this algebra to act on, so that you show that it doesn't collapse the whole story. So, sorry. Non-degenerate means this is a vague sense. So the category is not 0. I mean, so if you have, in general, if you define some algebra by generators and relations, there's no guarantee that very likely you will cook up the 0 algebra if you impose too many relations. Yeah. So, well, yeah, this is actually stronger, but yeah, maybe I should have erased non-degeneracy, but this is part of the proof that it categorifies UQSO2. All right. So, so what is the structure you have seen? So Lauda's calculus is really a two-dimensional idempotent algebra. So it has two compatible multiplication structures. So there's a vertical stacking, horizontal stacking, and this algebra is known as a two category. And I've seen from Phil's talk yesterday that this is a truly two-dimensional structure instead of well, you have an ordinary associative algebra. It's really a one-dimensional factorization algebra. But in this case, this is a really two-dimensional gadget. So let me just illustrate why this is. How to give you a sketch of proof why Lauda's theorem is true. So how does this one-dimensional picture back then for the quantum group case evolve into direct sum of this? So according to how we carry out categorification, this picture, one-dimensional picture, is represented by the class in the two-dimensional picture by left modules of this form, where the bottom has this form of E and F in the bottom. So this is isomorphism classes of modules in this of this form in the Grothendieck group will represent this one-dimensional picture. So how does this picture evolve into FE? So if you want this EF to evolve into FE, you have to stack some picture in the middle in the orange box I drew over there. So this box, this element will describe a homomorphism from this projective module to another projective module with FE on the bottom. So, so more generally, if you have to show some direct sum decomposition in the Grothendieck group, M is isomorphic to the direct sum of two modules. You have to construct maps from M into the direct sum and the projection and inclusion maps, satisfying these conditions, so the natural conditions, so that the compositions give you an orthogonal idempotence in the endomorphism ring of M. So you have a decomposition of orthogonal idempotence. So in this picture, really you can, because of the relations we have drawn, the natural way is just to split up the picture. We have seen one of the relations, and let me maybe recall this relation I drew over there, because in the middle it factors through this picture. So you can put the upper part, the upper part of this right hand side gives you evolution of this picture into the direct sum of things in the middle, and the lower part of the picture gives you evolution of the middle part back into this. And because of this relation, you can check that this gives you, these elements are a factorization of the identity homomorphism of this module. So therefore you have an isomorphism of EF equals FE plus a bunch of copies of shifted identities. Okay? Any questions? So these elements you can check using the relations I have written down earlier. They do indeed form the give you idempotent relations via composed with UI is identity I, and different ones are orthogonal, and the sum of this is the identity map of EF. So this is an orthogonal set of idempotents that gives you the corresponding decomposition. So we should call this maybe a factorization of idempotents that gives you the relation on the Grothendieck group level that is part of the defining relations of UQSO2. All right. So now borrowing what we have combining what Lauda and Khovanov-Lauda have done for the generic categorification case with what we have described for what we need at roots of unity is, let's try to enhance this entire picture with the P differential. So we want to have two category object in the homotopy category of P complexes. So therefore, the easiest way that this could work is you just equip this calculus, this two-dimensional algebra, with a differential D, P nilpotent differential that is defined as follows. So on generators, it's given by D of x equals x squared. This is D of a dot is dot squared, and D of a crossing is a crossing minus 2 times this guy. And similarly for the downward arrows, and on caps and caps, they satisfy this nice formula. So D of a cap is, it picks up a dot and a bubble with degree 1, a degree 2. Sorry. Yeah. Yeah. Yeah, that's a more intricate structure. Sorry, in the picture. Yeah, similar as to this relations. If you have e to the nth power, there is an idempotent in the neo-Hack algebra that gives you the e divided n. So, but that's described in the similar picture. If you have e to the n, n up arrows here, there will be maps from this to the corresponding idempotent module. Yeah, that gives you the divided power generators of Lutzdeck, if you know what they are, but if you don't, just yes, we have just technique. It's more technical that I didn't want to.
So when you were talking about the
yeah.
you didn't mention the divided by.
Yeah, I didn't, but this is for the small quantum group. You don't need divided powers at the moment. But if you have, quantum groups is a subtle business, especially at roots of unity, because when you want to specialize at root of unity, you have to have some integral form, and this integral form have to sometimes generated by divided powers. So there are many different kinds of quantum groups at roots of unity, the Concini-Katz or Lutzdeck or this idempotent inversion. So it's slightly subtle. I was trying to hide some details. So, all right, more questions? All right. So in this way, this is the definition is not so easy because it's defined on generators, but it's nevertheless a very small is a concrete computation, and you can show that this indeed is a p-nilpotent differential when you extend it by the Leibniz rule to all of this two-dimensional algebra U. So this D will preserve all the relations on U. You define it on the generators. You have to show that it sends relations to the ideal generated by relations, and it's p-nilpotent over a field of characteristic P. So yeah, linear category over a field of finite characteristic P. Yeah, here U is going to be defined over a field of characteristic P field. Yeah, well, technically you can actually do this over Z, but you lose pure nilpotency. Yeah, you can do this integrally, but for now, for simplicity, let's just work over a field of characteristic P. So, I can leave this lemma to you as an exercise. It's not very difficult. It's just practicing all the relations. It's a finite list of relations that you need to check that it's the differential operator actually preserve these relations. All right, so here's the main theorem that I want to discuss today. So it's built upon the work of my joint work with Khovanov and my work with Ben Elias. That's when you consider the PDG derived category of this should be compact modules over this two-dimensional or PDG2 category. It categorifies the idempotent form of UQSO2 at p root of unity. So there is an isomorphism of the Grothendieck group with the small quantum group. So I want to go into a little bit of technical details why this is true, just to compare with the abelian categorification by Lauda. So in this case, why some of the key relations in the defining relation of SO2 holds in the PDG world. So in the realm of triangulated categories, we're going to work with the compact derived category of PDG modules over U. So the direct sum decompositions are very rare. So usually in triangulated categories, you just have distinguished triangles glued together like those will impose relations on the Grothendieck group. So where do distinguished triangles come from in triangulated categories? For in the PDG world, just as in the DG world, they come from short exact sequences of PDG modules. So if you have a short exact sequence of PDG module maps, that gives you a distinguished triangle. So if you have a short exact sequence like this, in the derived category, it gives you a distinguished triangle. And in the on the Grothendieck group level, you have this relation M is the same as K plus L. Okay, so more generally, this short exact sequence can be regarded as a filtration of M by a submodule, which is K, and the quotient module is L. So more generally, if you have a filtered PDG module with some increase in filtration, then you get a convolution diagram or what's known as Postnikov tower of the associated graded. So this is extension of, you can regard M as an extension of these associated graded. So in the Grothendieck group, you would have this relation. So earlier we have seen in the abelian categorification case, you have a factorization of idempotents in the PDG algebra, and in the triangulated world, this is rarely the case. That's going to be a factorization of idempotents. But under some weak assumption, if there is a total ordering on this index and set, such that this is a partial, this vi times dui is 0 or ui times vdi is 0 modulo previous filtered terms, then the PDG module of A times this total idempotent admits a filtration whose subquotients are isomorphic to these guys. Okay, so in this, as a consequence, in this module in the PDG world, the symbol will be the sum of the symbols over here. And why this is the case? It's very easy to prove. Once you realize what you need to prove, you just need to introduce a filtration on the module A times epsilon. Epsilon is the sum. Recall, epsilon is the sum of all these idempotents, and you want to show that the associated graded are isomorphic to A times the other way of ui vi. Okay. So inductively, you want to show that this filtration is differential closed. It's closed under the differential, so it's an easy induction argument, and each of the subquotients are declosed, are under differential, and finally there is a PDG isomorphism. So I'll leave you as an exercise. This is an outline of the proof, which is not very difficult. So under this framework, so under the differential action on U, there is a filtration on EF and FE, and actually you just under differential, the earlier decomposition of the idempotent just becomes a filter diagram on this. So this is the F0 part is this submodule sitting inside U, and F1 you keep adding more and more term to the left. So the filtration becomes larger and larger, and you can use the previous proposition. You can check that this is these filtrations are preserved under the differential. So on the associated gradient level, you do have the EF relation on the derived category. Is this okay? This is again EF equals FE plus lambda times identity. Yeah, the only difference is that here you don't have a direct sum decomposition. Here you just have a filtration on the EF level. We do take Karoubi envelope, but it depends on what you mean by Karoubi envelope in the triangulated category. Yeah, you have an extra. Yeah, it doesn't respect the direct sum decomposition. It becomes a filtration. Yeah. EF of 1 lambda. This is the projective module where the bottom part is E and F, and the rightmost side is lambda. Okay, so now let's come to the key relation for showing that this is actually indeed a small quantum group. So this is, you want to show that this is the nilpotent. The key relation that's different from the generic case is e to the pth power should be 0 and f to the pth power should be 0. So why is e to the pth power and f to the pth power 0 in this case? So there's some preparation work that needs to be done before proving that. So inside Lauda's calculus, you before taking the differential, you always have this isomorphism of algebras. So endomorphism ring of the e to the nth power is isomorphic to the Neo-Hack algebra tensor with this ring of lambda. Lambda is the subalgebra generated by bubbles, positive degree bubbles. So it turns out you can identify this lambda with positive degree symmetric functions, so infinite variable positive degree symmetric functions. And each of these k is just degree 2k elementary symmetric function. So this is, or in other words, this is the cohomology ring of the infinite Grassmannian. So this is endomorphism ring of En is isomorphic to the Neo-Hack algebra tensor with this ring of bubbles. So the Neo-Hack part has an alternative description. This coming from geometric representation theory, very easy description. So this is endomorphism ring of the equivariant cohomology of the this is the GON equivariant cohomology of the flag variety over GON equivariant cohomology of a point. So this is so GON equivariant cohomology of the flag variety is just the polynomial ring in n variables, and GON equivariant cohomology of a point is the symmetric functions. So Neo-Hack algebra is just isomorphic to this endomorphism ring, where earlier the crossing operator is the divided difference operator, and the dots are just multiplication by term classes on the xi of the flag variety, the ith degree term class of how should I say, the line bundle of canonical line bundle on the ith step. So this is there you have this nice isomorphism, and when you impose a p differential structure on the entire story, so symmetric M becomes a PDG algebra, as we have said earlier, because the differential is symmetric, commutes with the symmetric group action. So this is a PDG algebra, and this has a PDG module structure over a symmetric group. So it has a d-stable basis as follows. We just take the first variable x1 to the I1, x2 to the I2, all the way to xn to the In, where ik satisfies between 0 and n minus k. So this is a size n factorial module. So from this, you can conclude that the endomorphism Neo-Hack algebra is n by n factorial matrix algebra over the ring of symmetric functions. So, and this module, now we have a PDG structure on the module generator. You can easily see under the differential we have written down. The differential will have this structure. So it acts on each variable individually. So this is just a tensor product of H representations like this. So whenever n is greater or equal to p, you see that there's the sum, this one of the free module summand will appear in the tensor product. Which one? Previous page. Where? Sorry. Generator. Oh, zero. This is just a placeholder. This is a rank 1 module over this polynomial ring. So this is just a generator, but it carries a differential in this way. Okay. Thanks for the good question. So this is so because of this generator, the H module or the P differential module structure is has this tensor product of representations that becomes larger and larger. But you see that from this picture, whenever n is greater or equal to p, one of these summands will be a free module. And remember, a free module tensor with any module is always free for Hopf algebras. So therefore, you can see that this module is always going to be a cyclic whenever n is greater or equal to p. So this is the things we have modded out. So now you can conclude that the Neo-Hack algebra over whenever n is greater or equal to p is is in a cyclic PDG algebra. So the nilpotency of this object will follow from this generalization of the classical theorem in DG algebra. So if you have a quasi-isomorphism of PDG algebras, then the restriction and induction functor induce an equivalence of the derived categories, a mutually inverse equivalences of triangulated categories. So in particular, if you have if you have a cyclic DG algebra, the inclusion of 0 is in quasi-isomorphism. So therefore, the Grothendieck group is just so the category just collapses, and the Grothendieck group is 0. Okay, so therefore, whenever n is greater or equal to p, the endomorphism algebra of this guy is a cyclic, so this object vanishes in the derived category. All right, I think there's a small surprise when you do in the abelian categorification, Lauda's factorization is not unique in general. So this is like the choice in an n by n matrix algebra. The choice of idempotents, indecomposable idempotencies are not unique. You can conjugate them by GON action. And so similarly, in Lauda's categorification, the factorization of idempotents is generally not unique. But in the presence of this diagrammatic local differential, so this differential we have written down is one particular case of them. Turns out up to conjugation by diagrammatic automorphisms, flipping diagrams upside down, there's a unique choice. So the differential defined is the unique differential that makes this categorification work. So this is a small surprise to Benilas and me. So, and Lauda's factorization of idempotents is also the unique choice that's compatible with the differential. And for this reason, we're shocked. So we call this a fantastic filtration on this category. And all right, I think that's a good point to stop, and that's all I have today.